All right, here we go. Welcome to our first lesson on momentum. All right, so, oops, sorry about that. All right, so today's lesson we're going to learn about the terms impulse, momentum, and basically how to solve problems dealing with these concepts. We're really going to focus more on the problems today, and we'll focus more on the concepts next time I see you in class. So anyway, here's your learning targets. These targets will obviously make more sense once you've watched the video, but I would recommend you take a second to read through them so you know what to watch for. All right, so here we go. So momentum. So I've never seen a great definition of momentum, a great concept-y definition of momentum. It's a tough thing. It's one of the few things that we learn about this year that you couldn't sort of explain to a third grader, right? Like velocity is how fast a thing is going, right? Basically, force is how hard you're pushing something. But momentum is a little bit more abstract than that, all right? So there's an author named Paul Hewitt who wrote a very well-known physics book that is used in many, many high schools. And he defines momentum as inertia in motion, okay? So a couple things. Symbol for momentum is the lowercase letter p, which is frustrating, but deal with it. So inertia in motion, well, what does that mean? Well, the big thing to take out of this definition is this. Remember, when we measure mass, technically speaking, mass is a measure of inertia. Okay, so the more mass something has, the more inertia it's got. All right, and basically, velocity measures motion, right? Because more velocity means more motion, right? So what Hewitt was saying is that the momentum of an object depends on the inertia, in other words, its mass, and on its motion, in other words, its velocity. Okay. And so because of that, usually the definition that I'll see in most textbooks is not at all conceptual, it's just a useless equation. Most books will say that an object's momentum is the product of its mass and its velocity, okay? So P equals mv. And unfortunately, that's really kind of the best definition, okay? Momentum is mass times velocity. That's what it is, okay? So, for example, here we go. We've got this 5 kilogram object. So our object has a mass of 5 kilograms. And it's moving along at a velocity of 4 meters a second, right? And so based on that, we can calculate its momentum. Momentum is mass times velocity, so 5 times 4 gives you 20. The units you get are kilograms times meters per second, which we say as kilogram meters per second. Okay, so there's the momentum. Now notice that same object, if it's sitting at rest because the velocity is 0, that's going to make your momentum equal to 0, right? So you have to have motion to have momentum, okay? Notice in this example, even when the thing is at rest, it still has inertia, right? Because it still has a mass of 5 kilograms. It just doesn't have momentum. All right? So let's dig a little bit deeper, all right? So as we just kind of illustrated, the momentum depends on the mass and on the velocity. So what that means is it's possible for different objects with different masses to have the same momentum. All right, so in this example, our little wiener dog here has a mass of 20 kilograms and a velocity of 8 meters a second. So his momentum is 8 times 20, so 160 kilogram meters a second, right? Okay. Our cow, meanwhile, cows tend to be slower, right? He's only going at 4 meters a second, right? So his momentum, sorry, 0.4 meters a second. So his momentum, or I guess her momentum, based on the anatomy here, her momentum is mass times velocity, so 0.4 times 400 gives you, again, 160 kilogram meters a second, right? So both animals have the same momentum, all right? Now, the other thing I want to point out about this example is momentum is a vector. Momentum has direction. Momentum is a vector, all right? And the direction of that vector is always the same as the direction of the velocity vector. In this example, my cow is moving to the left, which we have historically made a negative velocity, right? Well, that means that the momentum also needs to be negative, okay? So, both of these animals have the same amount of momentum, but the direction of the momentum is different, okay? Because the dog's momentum acts to the right, and the cow's is to the left. All right? All right there. So, all right. So note, for example, if the dog in that last example were to change his velocity, then his momentum would change, right? Because momentum is mass times velocity, right? So let's talk about change in momentum. So the symbol for change in momentum is exactly what you'd think it is. It's change in momentum, right? Well, anytime you find change in something, it's always final quantity minus initial quantity, right? Okay. Well, how would we find the final momentum of the dog? Well, that would be equal to the mass of the dog times his final velocity, right? And the initial momentum would be the mass of the dog times his initial velocity, right? Okay? Oh, I notice these both have m in them, so I can factor out an m and rewrite this as this. And I suppose if I wanted to, I could take it one step further and write it as this. Okay? So the idea is our change in momentum only occurs if there's a change in velocity. So you can calculate the change in momentum by multiplying the mass by the change in velocity. Okay? So that is going to become important. If you're curious why it says look at me over here, it just kind of gives us the same thing. Okay? All right, moving on then. All right, so let's do a quick example. This example, I'm actually going to do it using old equations, all right? I don't know, well, whatever, let's just do it. All right, so here we go. It says a soccer ball has a mass of 0.75 kilograms. It's rolling towards Roy. It doesn't tell us which direction that is, so let's assume that it's just rolling this way, all right? So the problem tells us that it has a mass of 0.75 kilograms. It's rolling towards Roy at 16 meters a second. Roy kicks the ball. Oh, that means my velocity is going to change. So this is just my initial velocity. Roy is kicking it the way it came from. So Roy is kicking this way with a force of 180 newtons. Notice that force here is going to be negative, right? Because the force is to the left. All right. The most common mistake this chapter is missing negative signs. Okay? I cannot emphasize that enough. Please, please, please watch your negative signs. All right, so Roy kicks this thing. He exerts a force of 180 newtons. It tells us that his foot is in contact with the ball for 0.15 seconds. And we want to find the final velocity. All right, so A says to make a free body diagram of the ball. So you're going to have Roy's force and then gravity and normal force, which cancel out. So we'll count that as being done. All right, part B wants us to find the net force. Well, our net force is just going to be negative 180 newtons, right? Because the only force affecting the motion really is Roy's force, right? Okay, well, so then for part C, we can find the acceleration. Acceleration is net force over mass, so negative 180 newtons over 0.75 kilograms gives us 240 negative meters per second squared, right? Because the velocity of the ball is going to change very quickly under the force of Roy's foot. So then D wants to know what final velocity he'll reach. So we'll just do VF equals VI plus AT. So let's see, our initial velocity was 16. Acceleration is negative 240. Time is 0.15 seconds. Multiply this out and you end up getting negative 20 meters a second. And the negative is telling us that it's moving to the left after he kicks it, just as you would guess. Okay, so this is, you know, whatever, first semester stuff. Hopefully that's, you know, pretty straightforward. Okay? So it turns out there's another way to do this problem, which is we can also solve this using impulse and momentum. All right? So let's do this. So note, we already know two different equations for acceleration, right? We know from the beginning of the year the definition of acceleration. Acceleration is Vf minus Vi over t, right? Okay? We also know from Newton's second law that acceleration is net force over mass. So if A equals B and A equals C, then B equals C. So now we've got Vf minus Vi over t is equal to net force over mass. I have two fractions that are equal to each other. I can cross multiply, and you get this. Net force times time equals mass times Vf minus Vi, right? This is by cross multiplying. Oh, and this thing here, this is my change in momentum, right? Okay. Now, this quantity over here is often called impulse. Okay? I always get frustrated with this, that anybody even gave this a name. Because this equation proves to us that impulse is simply equal to the change in momentum. All right? So some books give impulse a symbol. They use the capital letter J. And then this is like a big important theorem that, oh, impulse is equal to change in momentum. I don't even know that I want you to distinguish between the two. Okay? So this is a little sloppy. I'm sure there's a physics professor somewhere that's going, what are you doing? You can't do that. But I'm going to do it anyway. Definition of impulse, change in momentum. all right? And there are two ways you can find the impulse. You can either do net force times time, or you can do mass times change in velocity, okay? So impulse is a change in momentum, okay, by definition, all right? So that is that. So we have two ways now to find our impulse, net force times time or mass times Vf minus Vi, okay? I'm going to finish coloring this in because somebody's bothered by the fact that I haven't highlighted everything. There we go. We're good. Oh, okay, phew. Oh, all right. I just spent time on that. Okay, so there we go. So impulse and change in momentum are the same thing. Whenever you hear the word impulse, you should think, oh, that just means change in momentum, and then move on. All right? So let's see if we can use this new equation to solve that problem again. All right? So I just came up with this equation, right? Net force times time equals mass times change in velocity. So in this problem we just did, here's what we know about the soccer ball. We know that the mass of the soccer ball is 0.75 kilograms. All right? I'm not going to draw it again because we already made a drawing, but ordinarily if I was starting this from scratch, I would draw it. All right? We know that the initial velocity of the soccer ball is 16 meters a second. We know that the force on it from Roy is really the only force, so our net force is negative 180 newtons, right? We know that that net force is going to act on it for 0.15 seconds, and we're looking for our VF, right? So most of your problems on this first homework assignment are going to be these 5 variables. I'm going to give you 4 of the 5, and you got to find the missing one. All right, so that's kind of it. No big deal. All right, so to solve this thing, we're going to go net force times time equals mass times change in velocity. Let's plug in our numbers. So our net force is negative 180. Our time is 0.15 equals our mass, which is 0.75 times Vf minus Vi. Okay, and solve it. All right, so 180 times 0.15 gives you negative 27 equals 0.75 times Vf minus 16. All right, and at this point you've got two choices. For whatever reason, I always see that students like to distribute this, which if you want to do that, cool. That is not how I usually do it though, because that feels like extra steps to me. So what I'm going to do is this. Let's divide both sides by 0.75. Okay, and then you get negative 36 equals, these guys cancel, Vf minus 16. Add 16 to both sides, and your Vf is negative 20 meters a second. All right, so there we go. We got the same answer, right? Okay, so that's that. So the obvious question, well, okay, so let's take a second and what have we learned? All right, so here's a quick summary. Momentum, product of mass and velocity. Impulse, change in momentum. And here's all of our equations. This bottom one can be rewritten as net force times time equals mass times Vf minus Vi. It is a frequently useful tool. All right? And so, you know, it simplifies problems, right? Okay, so here's one other quick example. So let's do this. So we got a 40 kilogram shopping cart. All right, it's rolling towards your car at 18 meters a second. You've got a time of 3 seconds and you want to stop it. And the question is, how much force do you need? Okay, so we're just going to do the same thing. Net force times time equals mass times Vf minus Vi, and plug in the numbers. We got to find the net force. Time is 3, mass is 40, Vf is 0, Vi was 18. So solve, and you end up getting negative 240 newtons. There you go, there's your answer. Okay? So I kind of plowed through that example because ultimately, like if somebody just walked up to me on the street and said, hey, Mr. Hacker, solve this problem, I would not do it using conservation of momentum, or using, sorry, impulse and momentum. I would do it using Newton's second law. I would find the acceleration and then multiply by the mass, okay? And it amounts to the same thing, right? Because your acceleration is 6 times 40, you get 240 again, all right? So the big question then is, why do we care about all of this garbage, all right? And so that's going to be the focus of our next lesson. It allows us to answer some questions in a slightly different way than we would have done before, and provide some insight into some concepts, That's the worst sentence ever said. I'm going to stop there. We're going to learn why we care later. All right, there you go.